We will now continue solving slope and deflection of beams using the conjugate beam method. Today, we will deal with another non-prismatic beam, since as we can observe, the relative moment of inertia of the inner portion of the beam is twice of the relative moment of inertia on the outer part of the beam. The requirement of this beam is to solve for the maximum deflection using the conjugate beam method. Just like what we did in our previous problem, we will follow some simple steps in order to solve for the problem. The first step is to write the working equation. The second step is to solve the support reactions. The third step is to draw the M/EI diagram and the corresponding conjugate beam. For the fourth step, we will solve for the properties of M/EI diagram. And finally, on the fifth step, we will solve for the unknown. We will now start in step number 1. We write the working equation. Say that the location of maximum deflection is at point F of the beam, so that maximum deflection will be equal to the deflection at point F of the beam. From the relative properties of real beam and its conjugate beam, we have learned before that deflection on real beam is equal to the corresponding bending moment on the conjugate beam. So to find for maximum deflection, we have to find the maximum moment on our conjugate beam, and that is the moment at point F on our conjugate beam. So we can now say that delta F is equal to MF. And here is now our working equation. Then we will proceed on step number 2. We will solve for the support reactions. Applying equations of static equilibrium, summation moment and summation forces along vertical is equal to 0, we can be able to solve for AY and DY. Applying summation moment at point D, we can solve for the value of AY, and that is just equal to 100 multiplied by the distance from point C up to point D, which is equal to 5 meters, plus 200 multiplied by the distance from point B up to point D, which is equal to 15 meters. Then we divide it by the distance from point A to point D, that is 20 meters, and AY can be obtained, that is equal to 175 kilonewton. Applying summation moment at point A, we can be able to solve for dy, and that is just equal to 200 multiplied by the distance from point A up to point B, that is equal to 5 meters, plus 100 kilonewton, the concentrated load at point C, multiplied by the distance from point A up to point C, which is equal to 15 meters. Then we divide that both into 20, and the equivalent is equal to 125 kilonewton, the vertical reaction at point D of the beam. If we add AY to DY, 175 plus 125, that is equal to the applied load, 200 plus 100, which is equal to 300 kilonewton. We will now proceed on step number 3. We will draw the M/EI diagram and the corresponding conjugate beam. In our previous example, we make use of the moment diagram by parts, or the equivalent cantilever beam, in constructing the M/EI diagram. But at this time, since we have a concentrated load, we can simplify calculation, since we have only a first degree curve at any segment of our bending moment diagram. It simply means that if the real beam is subjected by a concentrated load, we can make use of the conventional bending moment diagram as our M/EI diagram, or the bending moment diagram of the beam, which is constructed from the area of shear diagram of the beam. So to solve now for the maximum ordinate at point B and point C of the beam, that is just equal to the reaction at point A multiplied by 5 meters. 175 multiplied by 5 is equal to 875 kilonewton meter. And for the ordinate of bending moment at point C, that is just equal to the support reaction at point D, which is equal to 125 multiplied by the distance from C to D, that is 5 meters, and it is equal to 625 kilonewton meter. After solving for the ordinate of bending moment at point B and point C of the beam, we can connect it with a line, and here is now our bending moment diagram. We cannot apply this technique if the load is uniformly distributed, since if the load from point B up to point C is a uniformly distributed load, we can have a second degree curve from point B up to point C. And to solve for the properties of the area under a second degree curve in this situation will be more tedious and complicated, since we have no direct formula to solve for the properties of that area rather than integration. On those cases, we have to apply the technique we have learned in constructing M/EI diagram by parts by using equivalent cantilever beam, selecting any point of the beam as our fixed reference line. We will now proceed. Since the relative moment of inertia at point B up to point C of the beam is twice of the relative moment of inertia of CD and AB, we have to divide 875 kilonewton meter and 625 kilonewton meter into the relative moment of inertia. And 875 divided by 2 is just equal to 437.5 and 625 divided by 2 is equal to 312.5 kilonewton meter. And it will be the ordinate of the M over EI diagram of the inner portion of the beam. It means that we will only consider the properties of the shaded area in solving the maximum deflection of the beam. But since the inner portion is trapezoidal, since 437.5 is greater than 312.5, let me divide this area into two areas. That is a triangular area and a rectangular area. After constructing the M over EI diagram, we can now draw the conjugate beam of our real beam. From relative properties of real beam and its conjugate beam, the simple support located at the ends of real beam remains as simple support for conjugate beam. So as we can observe, we have a hinge support at point A and a roller support at point D. It will remain to be hinge and roller on our conjugate beam. And from property number 1, the length of real beam and conjugate beam are equal to each other. So if our real beam have 20 meters length, then our conjugate beam is also 20 meters. So here is now our conjugate beam in solving for the problem. From property number 5, the load on the conjugate beam is equal to the M over EI diagram of the real beam. So we can now apply the M over EI diagram of our real beam into our conjugate beam as a load. So here is now our conjugate beam loaded by the M over EI diagram. Our aim is to solve for moment at point F of our conjugate beam. Let us now focus our attention to this beam. How can we solve for that bending moment at point F of the beam? It will be a simple problem to us if the location of point F from point D is given on the problem. We can just pass this cutting plane A dash A, then we can apply summation moment at point F, then we can solve for the bending moment at point F of this beam. But since the distance from point D up to point F of the beam is still unknown on the problem, we have to find our ways on how to solve first for this distance x. And from the principles we have learned in constructing shear and bending moment diagram of beam, we have learned that the location of maximum deflection is at the point where shear is equal to 0 in our beam. And to solve for that unknown distance x, the location of 0 shear on the beam, we have to write the shear equation and equate it to 0. And after solving for that value, we can now apply summation moment exactly at this point. By passing a cutting plane A dash A, we can now solve for moment at point F of our conjugate beam. But before we can write the shear equation, we need to solve first for dy, since it is very involved if we pass cutting plane A dash A and select the right part of cutting plane. As our free body diagram, dy is very involved in writing the shear equation. So we have to solve first for dy. By applying equation of static equilibrium summation moment at point A of this beam, we can be able to solve for dy. After solving the values of area 1, area 2, area 3, area 4, and the corresponding moment arms x bar 1a, x bar 2a, x bar 3a, and x bar 4a, we can solve for the value of dy. We can observe also that we have considered the location of the M over EI diagram. Since our M over EI diagram is located on the positive side or above the neutral axis, it is applied in upward direction into our conjugate beam. So the ordinate at point B is equal to 875 kilonewton meter. The ordinate at point C is equal to 625 kilonewton meter. Half of 625 is equal to 312.5 kilonewton meter. And since we divide the trapezoidal area from point B up to point C into two areas, triangular and rectangular, the ordinate of triangular area is equal to 437.5, that is half of 875, minus 3125, that is half of 625, and that is equal to 125 kilonewton meter. We will now solve for the properties of M over EI diagram in order to solve for the unknown support reaction at point D, that is dy. We will start solving the properties. Since area 1 is a triangular area, we can solve that from the simple equation 1/2 of base multiplied by height, wherein the base distance is equal to 5 meters and the height is the ordinate of M over EI diagram, that is 875. We divide by 2, and that is equal to 2187.5 kilonewton meter square all over EI. And for area 2, that is also triangular, the maximum ordinate is equal to 125 and the base distance is equal to 10 meters. 1/2 of base multiplied by the height is equal to 125 times 10 divided by 2, and that is equal to 625 kilonewton meter square all over EI. For area 3, that is a rectangular area, and the ordinate is equal to 312.5, and the distance where it's located is 10 meters. So 312.5 times 10 is equal to 3125 kilonewton meter square all over EI. For area 4, that is also a triangular area, we can solve that from the simple formula 1/2 of its base multiplied by height, wherein the height is equal to 625 kilonewton meter, base distance is equal to 5 meters, divided by 2, and that is equal to 15625 kilonewton meter square all over EI. By applying summation moment at point A, we need the distance of each centroid from point A of the beam. Since area 1 is a triangular area, the location of its centroid from point A is just equal to 2/3 of its base distance, that is 5 meters. So 2/3 of 5 is equal to 3.33 meters. For x bar 2A, that is located at 1/3 of its base distance, that is 10 meters. So 1/3 of 10, then we add the distance from point A up to point B, which is 5 meters, that is equal to 8.33 meters. For x bar 3A, that is located half of the base distance, that is 10 meters, plus the distance from point A to point B, that is 5 meters. So 5 plus half of 10 is equal to 10 meters. And for x bar 4A, that is located at a distance 1/3 of its base distance, that is 5 meters. So 1/3 of 5 is equal to 1.66. Then we add 10 meters from point B up to point C. Then we add another 5 meters, that is from point A up to point B. So the centroid of area 4 up to point A is just equal to 1/3 of 5 plus 10 plus 5, which is equal to 16.67 meters. After solving the properties of M over EI diagram, we can now apply summation moment at point A in order to solve for the unknown reaction at point D, that is dy. Applying summation moment at A is equal to 0. We have dy multiplied by the moment arm, that is equal to 20, is a clockwise moment with respect to point A. And area 1 multiplied by its moment arm x bar 1A is a counterclockwise moment with respect to point A. That is negative in our equation. For area 2 multiplied by x bar 2A, that is also a counterclockwise moment with respect to point A. Area 3 multiplied by x bar 3A, that is also counterclockwise with respect to point A, and that is also negative in our equation. For area 4 multiplied by x bar 4A, that is also a counterclockwise moment with respect to point A, it is also negative in our equation. Then we will replace the value of area 1 x bar 1A, area 2 x bar 2A, area 3 x bar 3A, and area 4 x bar 4A in our equation. And from this equation, we can be able to solve for the value of dy, and it is equal to 3489.56 kilonewton meter square all over EI. After solving for dy, we can now pass cutting plane A'. We select the right part of the cutting plane as our free body diagram to write the shear equation of the beam. So here is now our free body diagram, right portion of cutting plane A' as our FBD. Say that the portion of a triangular area to be area 5, the portion of the rectangular area to be area 6, and area 4 will remain. At this point, shear is equal to 0. In other words, we are finding the value of x from where the M over EI diagram will give us a total area equal to 3489.5625 if we add area 4 into area 5 and area 6. Say that the ordinate at the point where we pass cutting plane in the portion of the triangular area to be y, and we can solve for this value of y by similar triangle, since we have 125 is to 10 meters and y is to distance x, from where we can solve for the value of y, which is equal to 12.5 multiplied by x, and say that is equal to area 5, and for the rectangular area that is area 6, from where we can solve for the value of area 5 in terms of x, and that is just equal to 12.5 x multiplied by the distance of its base, which is equal to x. Then if we divide by 2, that is equal to 6.25 x squared. And for area 6, that is just equal to 312.5 multiplied by the base distance, that is x. So that is equal to 312.5 multiplied by x. So dy, the downward force reaction at point D, is equal to area 5, that is upward, area 6, which is also upward, and area 4, which is also upward. And we have already solved for the value of area 4 from our previous calculation, that is equal to 1562.5 kilonewton meter square. We can now replace the value of area 5 and area 6 in terms of x in our equation, and area 4 into 1562.5 kilonewton meter square. Then we can solve for the value of x from this equation, and that is equal to 5.5 meters. That is the location of zero shear in our conjugate beam. So after solving for that value of x, we can now replace the value of x into area 5 and area 6 to solve for the numerical value of area 5 and area 6. And that is just equal now to height, which is equal to 69.375, since 12.5 multiplied by 5.5 is equal to 69.38 or 0.375. If we divide by 2, because that is a triangular area, it will be equal to 192.52. And for area 6, that is rectangular area, 5.5, the value of x, multiplied by 312.5, that is equal to 1734.38. And the value of distance from point F of the beam, since we will apply summation moment at point F, we need the distance from the centroid of area 5, area 6, and area 4 measured from point F. And for area 5, that is called x bar 5F, and for area 6, that is x bar 6F, and for area 4, that is x bar 4F. We can now solve for the values of those distances. For x bar 5F, that is 1/3 of 5.55, since that is a triangular area, so it is equal to 1.85 meters. For x bar 6F, that is equal to 5.5 divided by 2, since that is a rectangular area, so it is equal to 2.775 meters. And for x bar 4F, that is equal to 1/3 of 5 meters plus the value of x, which is equal to 5.5 meters, and it is equal to 7.217 meters. After solving for those properties, we can now apply summation moment at point F is equal to 0 in order to solve for the bending moment at point F of our conjugate beam. So we have now dy, that is clockwise moment with respect to point F, multiplied by the distance moment arm, 10.55 meters. Area 4 multiplied by x bar 4F, that is counterclockwise with respect to point F of the beam. Then we have area 5 multiplied by x bar 5F, that is also counterclockwise with respect to F. Then we have area 6 multiplied by x bar 6F, that is also counterclockwise with respect to point F. So those are negative in our equation. Then if we replace now the value of area 4, x bar 4F, area 5, and x bar 5F together with area 6, x bar 6F, and the value of dy from our previous calculation, which is equal to 3489.56 kilonewton meter square all over EI, we can have now the value of MF, and that is equal to 20369.8 kilonewton cubic meter all over EI. Since MF, the bending moment at point F of our conjugate beam, is equal to the deflection at point F of our real beam, deflection is equal now to 20369.80 kilonewton cubic meter all over EI. Since E is equal to 200 megapascal and I is equal to 4 multiplied by 10 raised to 8 millimeter raised to 4, we can replace now the value of E and I in our equation. To be consistent, we have to convert kilonewton cubic meter into Newton cubic millimeter by multiplying 1000 raised to 4 in our equation. Then we can see that kilonewton cubic meter will become Newton cubic millimeter, and for Newton and Newton it will cancel out. Millimeter raised to 2 into millimeter raised to 4 will be squared, then squared into cube. What is left is mm, and that is our unit for the deflection at point F of our real beam, and that is equal to 254.622 mm. So I hope that you have learned a lot from this example. To those who want a copy of this file in PDF, comment down below your email ad, like and subscribe, and I will send it to you. Thank you.